So the title of my talk is Euclidean distance matrix completion with one missing node. So this is a joint work with Stefan Sremich, Henry Walkwith, and Lucas Peterson. So the background of the problem is so we consider this single source localization problem. So the problem is the following: we are given n sensors. The sensors are, or we call it towers. So the towers can they can send signals and receive signals, and we have a source which is a cell phone in dimension R space, and we assume that the location of the sensors are known and given by this matrix PT, and we assume that the distance between the source and the sensors are contaminated with noise. So di is equals to di bar plus epsilon I, where di bar is the true distance, and epsilon r is the perturbation or noise. So and then the problem is to locate the source as accurately as possible to find the best approximation for the true location of the source on the cell phone. So we consider three models. First, the first model is we fix the distance between the sensors or the towers. And the second model, we allow the sensor to move. So the sensors are flexible, but they are not completely flexible. So the sensor can be translated into its original position by an invertible matrix. And the third model is we allow the sensor to move completely free. And then we will compare these three models and see which one is performs the best. So first, we consider the first model. So the distance between sensors are fixed. So so the basic assumption is the following. We assume that the number of the sensors and the towers is greater or equal to r plus 1. And we assume the interior of the convex hull of these sensors is not empty, and the sensors are centered. So using this Euclidean norm as a metric, we will obtain the least square problem, right? So this problem is the following: we minimize the summation of the square of the differences of the distances. So this solution of this problem is the maximum likelihood estimator when the noise is assumed to be normal and the covariance matrix is a multiple of the identity. But this matrix, this problem is non-convex and non-differentiable. So instead, we apply this squared trick. So we consider this a different problem, SOS. So where the distance are squared. So x minus pi is squared, di is squared, and then we have the square of a square distance. So this is called a squared least square problem. In this problem, all these the only unknown is x. So x is the location of the source, and all these sensors or towers are given, and their equation are fixed. And this problem SOS is is equivalent to this GTRS, the generalized trust region subproblem. So we can do a simple substitution using the S squared is equals alpha, and this and we consider this we can convert this problem, the SOS problem, into a standard trust region subproblem, and the strong duality is proved in these papers. The SOS is equivalent to GTRS. That means that their optimal value is the same. And the rank of A and the optimal of GTRS is finite and attend. And strong duality holds for GTRS. Dual value is attend. So we will develop an approach based on SDP, semi-definite programming to solve this GTRS problem. The problem is although this optimal of GTRS can be it's finite attend and can be computed by the SDP by its SDP reformulation, but the optimal solution may not be rank 1. So that's the problem. So we have a we have a purification algorithm to actually reduce the rank and actually get the rank 1 optimal solution of the SDP problem. So now how can we convert this this GTRS or the dual problem of the GTRS 3 into an SDP, which is the following SDP problem, and we define a map. So this map Uy is equal to Y1 times Y1 transpose. So the rank of the matrix of the image of the map is always 1. So let omega denotes the optimal set of the solutions of SDR. We have the following optimal value of the GTRS SDR are all equal, finite, and attend. And secondly, the matrix S star is an extreme point of the optimal set. If and only if Y star is equal U minus X star for some minimizer Y over GTRS. So that's if GTRS has a if we find a minimizer of Y, and then there is a corresponding extreme point in the SDP relaxation SDR. And in addition, this we can using the Padaki equality, we can prove that this extreme point of omega is always rank 1, because there is only two constraints. There are only two constraints. And then apply this Padaki equality, we can prove that the extreme point is 1. The rank of the extreme point is always 1. So that said, if we have found an extreme point, if we have a rank 1 solution, if we can find a rank extreme point of omega, then immediately we can find a minimizer of the GTRS problem. If we cannot find a extreme point, we need some approach to actually reduce it to an extreme point. In addition, there are 3 and 4. 3 sets if the GTS is a unique minimizer, then the optimum set of SDR is a singleton. And 4 sets if the optimum set is a singleton, and then the GTRS is a unique minimizer. So based on 2, the probability 2, we have a purification algorithm. So if we do not have an extreme point of the SDP relaxation. So how we purify it? The idea is it's simple, right? So we actually we just add a new constraint. So this A bar S equals to PS star SDR. So by applying this constraint, we are restricting the problem to the optimal set, because this is exactly the optimal value of the SDP problem. So and then we add this when we add this constraint. So the problem is always is optimal of the original problem. And then we choose the C in the non-space of the AS excluding 0. Then we have this rank reducing problem. This problem has the property that it's the optimal solution. It's always rank deficient. So it's always rank not full rank. So therefore, when we solve it, we reduce the rank by at least 1, and then we continue. Each time the rank is reduced by 1. So after at most R+1 iterations, we can purify to get an extreme point, and then we solve the DTRS problem. So here is some lemma, lemma 1, and this is the purification algorithm. The idea is it's just the key idea is to find the CK which is in the non-space of ASK 0, and then solve this problem. And this problem, the solution of this, the optimal solution of this problem, it will be rank deficient. So compared to the approach by Baker, we do not have this hard case. We can actually we do not differentiate between hard case and easy case. We just solve this SDP relaxation. So this is the model that of the fixed towers, fixed sensors. And secondly, I want to talk about this the other 2 models, right? Where the first model is so this is actually related to the EDM completion problem. So the EDM the corresponding EDM is denoted as DT, and is defined as by DT IG. It's the distance between points, and the approximate EDM for sensors and the source is DTC. So here this D Hadamard D is contaminated distances. So the nearest EDM problem with fixed sensor is the following. So we minimize this problem, and this is the EDM with fixed sensors. And if we relax this problem, we drop this we drop this rank constraint, and we ignore the towers. So we have a nearest EDM problem. So this is called nearest EDM. So we minimize kx minus dtc square, and rank x is less equal to r. X is a positive semi-definite. And the K is the map between the PSD cone and the EDM cone. So in this model, the towers are completely free. So there's no restrictions on the towers, the location towers. So towers are treated the same as the source, as the cell phone. Or the sensors are treated. Sensor towers are treated the same as the source of the cell phone. We can actually restrict this problem to a face. So actually, if we allow x, if we require x to be in the face of the of this face, so where ft is the following. ft is xt is the set of all the PSD such that it's a EDM is projected to the EDM of the towers. So the true EDM, the true ground matrix, so which is from the towers and the true location of the source belong to this set. So we restrict, we add a new constraint such that this, instead of in addition to the nearest EDM formulation, we require x to be in this phase So if x is in this phase, it has the property that after we solve this, we procrast this this problem, the tower can be exactly rotated back to its original location by an invertible matrix. So the matrix is not necessarily an identity, but it's invertible. So the towers can be put back if x is in this phase. So and the closed form expression for this phase is the following. So GT is the ground matrix for the towers, and then we just apply the spectral decomposition to the ground matrix, and we find an exploding vector, and with exploding vector, we can apply facial reduction and get a facial reduced problem, which is the following. Here, so here this is x is replaced by kvr, whereas kvr is obtained by applying the facial reduction, and h alpha is the weight. So we add a weight. So how do we solve this problem? So theorem 4 says that theorem 4 basically says that it said this when we solve this FNEDM, is the towers can be rotated back to its original position. So that's theorem 4. So how do we solve this problem FNEDM? So there are 3 cases. So this problem is not a convex because there's a rank constraint. So the rank R, big R, is less or equal to small r, and the size of the R is actually R plus 1. So there's a so the rank is one less than the size of R. So that means the optimal solution has to lie on the boundary of the PSD cone. So you can replace this constraint by saying R has to be on the boundary of the PSD cone. So there are three cases. The three cases are differentiated by the solution of the least square problem. The least square problem is this problem without this constraint. So without this rank constraint, without this PSD constraint. So we solve this least square problem, and if a solution is if a solution is already positive semi-definite and the rank is less or equal to R, then we are happy. In the second case, if the solution is not actually a PSD matrix, then again we are happy. And case 3, RLS, is the solution of the least square problem is strictly positive definite. So case 2 and case 1 and case 2 can be solved by simply dropping out the rank constraint. So they are the easy cases. And so case 3 is a hard case. The case 3 is how we so to solve case 3, we actually we use this. We are motivated by the primal dual and penalty approach by Qihou Duo and Yuan Xiaoming and Sun Defeng and these guys. So the approach is called the rank majorization approach. So the idea is to add a penalty term here, and each time we differentiate this penalty term and obtain UK, and we add we linearize this penalty term. Right? This penalty term is a non-convex term. Therefore, we linearize it. So replaced by PRK plus UK inner product R minus RK, and then and update R UK after each solving each problem. So there's a nice theory about this approach. It says if this rank majorization algorithm converts to the stationary point R bar, and the stationary point is actually happen to be R, and then R bar is a global minimizer of the feature reduced nearest problem. So although we cannot guarantee that this is always converted to the global minimizer, but we can check. So we have a condition that we know that. So there's a condition that we can check if it's indeed a global minimizer of the NEDM. So this is the hard case. This is the hard case solved by the can be efficiently solved by the rank majorization approach. Okay, so one advantage of this feature reduced problem is that we can identify the outliers using the L1 minimization and the facial reduction. This is because by facial reduction, the problem size, the size of the problem is reduced, but the number of the constraint is not reduced. So therefore, there are more constraints than variables, and we can use the L1 minimization to identify the outliers. So the outliers are the towers, the distances that are like very that are contaminated by big noise. So most of the noise are kind of a Gaussian noise or something, or small noise. But maybe for example, if a tower is blocked by a building or something, or the tower there's something wrong with tower, then the errors can be, then this error of the distance can be very big. So removing this outliers is important to get accurate estimation of the source. And this is done by can be done by the facial reduction approach. And the L1 minimize. So we consider this problem. So we minimize the delta or norm such that the delta is the error, the error of the of G. So minimize the L1 norm of the error, and subset the G the S2 the matrix form of G is a positive semi-definite. This will and the error and in this delta the big components, if delta I is big, then the ith tower will be an outlier. So we remove the tower. So we have a algorithm 3, which is used to remove the outliers. The input is the matrix of sensor locations and vector of noisy distances. First, we solve the following L1 norm minimization problem. Minimize this KVR minus DTC L1 norm such that R is a positive definite. And then obtain this error term. And then we normalize it. And then we remove these towers from PT and TI from D for all these i's, satisfying that I is greater or equal to a threshold. And the output is the sensor matrix PT and distance vector D with outliers are removed. So after outliers removed, and we can so how do we recover source location from the grand matrix? So we have two approaches. The approach 1 is the crust approach. So we solve the following procrust problem. Minimize PT minus PF bar Q, such that Q transpose Q is an identity. So PT is the towers, and the PF is the what we get by solving the by optimization. So and then we want to recover it such that PF is as close as to PT, and Q has to be a rotation matrix. Approach 2 is we do not require Q to be a rotation matrix. So Q is just any invertible matrix, and because X is in the face of the true Gram matrix. This guarantees that the minimizer of the optimal value of this is always 0. So we can actually exactly recover the towers. so there's there are two approaches. So we have talk about three problems, three models. One is the SDR model, which means that the towers are completely fixed. Second model is the EDM model, the nearest EDM. And this can also be solved by approach using the semi-smooth Newton method, and developed by Ho Qi and other guys. So, but we do not discuss how to solve this, but we use other people's code to solve the nearest EDM. And the third model is the facial reduced nearest EDM model. So now and then we compare the three models and see which model is the best to recover the true location of the source. So we use the randomly generated data with an error proportional to the distance to each tower, and the error is given by and the proportionality is given by eta. So and eta is the so the error epsilon is in the is a uniformly generated data as lies between minus lambda and lambda. With different error proportionality, here is the numerical result. So the first column is the eta, and the second column is the number of sensors, and we report the error in each column. So in this table, there's no outlier. So you can see that in most cases, the F and EDM is actually quite good. Right here, here in the first column, the F and EDM P means so we procross this problem, and L is the least square approach. There are two approaches to recover the towers for each model, for the EDM model and for the F and EDM model. But for the SDR model, because the tower are fixed, we do not distinguish between the procrast or least square approach. With all these approaches, it seems that FNEDM is the best approach. So for different eta, so to actually compare the approach, out of the approaches, we compute the performance. We use the performance profile actually. So the performance profile is and we can see the performance profile is the following. So here I have two figures for different eta. So for different level of noises, and the one on the in this first picture, the black curve, the black plot is the best because it's lies on above all the other approaches. So the black is is by procrast the FNEDM model, and the second better one is the SDR. It's by fixing it's by fixing the towers, and I think the LNEDM, the least square approach, is not actually, I think what's the performance profile? I think that it's which one is so so I think it's the LEDM is the best, right? Performance profile is the one that's on the top is the best. Or let me check. Yeah, actually, actually, in our performance profile, so the performance profile is the ratio of Cn eta m. This Cn is the mean over all the 100 distances for n towers, and this function is it's given by this ratio, such that the performance ratio is less or equal to gamma. So when this function is smaller, that means the error is small. So here's the performance profile for this function with no outliers.
I think the yes, but the one on top is the best, right? So this is the one on top is black. So is PFNEDM is the best.
Yeah. Yeah. Yes. Yes. Smaller values of this implies a better performance, and the function phi m measures how many pairs were solved with the performance ratio are better. I think, yeah, so the function is monotonically non-degrading and large values are better. Yeah, so the one on the top is better. So the black one is the best and the blue one is the worst. So you can see the by cross the FNEDM, this gives the best, and the blue one is the nearest EDM. With this means allowing the sensor to be the towers to be completely free. Is the worst, and the least square approach is the blue one. It's the yellow one is the least the second worst, and the SDR is actually by fixing the sensors actually it's actually the second best. So that's the conclusion. We compared this other approaches and we found that the facial if we give some freedom to the towers or the sensors, and then we process it actually had the best performance than fixing the towers or allowing the towers completely free. So that's the end of my talk. Thank you for your attention. And here are some references. Yeah, this is the reference. This is the reference for solving the, where is that? Yeah, this is the method we use to solve solve the nearest EDM problem, and also the rank majorization approach. And here is the trust region subproblem paper by Henry and Pinky. Where is that? Yeah, this is paper. So now. So I think now it's time for questions.
Thank you. Thank you, Faye. So, any questions? So I was wondering, I don't know if you, I think, yeah, you were here about the talk yesterday about with the lawnmower. So the lawnmower talk essentially had the lawnmower as, it seems, sort of a similar problem. The lawnmower can be considered as a single source, and the anchors which were in the lawnmower problem can be thought of as the towers here.
Mm-hmm. Yeah.
So in some sense, it's a similar problem because the application is for the single source being a cell phone, right?
Mm-hmm.
So what would happen if you made this problem dynamic? The cell phone started moving. Is it possible? I mean, it seems just this problem. So if the cell phone started moving, I guess you would need some sort of functions to approximate the path.
Yeah, I see.
Some basis functions.
Yeah. So, yeah, this is as a so we can actually to track this the source dynamically.
Yeah.
Yeah.
Would that be better than just finding the position each time?
Yeah.
I guess then you could even think about predicting where the cell phone is moving in the future. I'm not sure if that makes sense.
Mm. Yeah.
Google at the moment is telling us which restaurants we go to. They can then predict what restaurant we will go to.
Yeah. So yeah.
So the green, the SDR, that was when all of them were fixed.
Yeah.
And it did so well.
Yeah, it did actually quite well. Yeah, it's better than the EDM. So yeah, I think I was thinking I expect that the nearest EDM is better than SDR, but it turns out SDR is better than the nearest EDM approach.
Does anybody else have a question? I'm monopolizing here. Can we see the SDR model again?
SDR is this yeah. Just SDP relaxation of the trust region subproblem. Yeah.
Also, can we see equation 12 again?
Help?
Yeah. Okay. And I guess more, sorry, and 17. Yeah. So this P of R is a non-convex. What is P of R?
P of R is the it's the what's P of R? Yeah. Let me see what is PFR. It's let me write on the screen. It's a PR is a I R minus the lambda I. So it's a concave function. So you actually want to penalize the residue of the eigenvalues. So here I have only this is not M. This is actually R. This is actually R. So because I wanna, and this is the lambda I is the ith eigenvalues, and this is the trace of R, right? So this is all the sum of all the eigenvalues, sum of all the R plus 1 eigenvalues, and this is
so that's like a well, it is. It's the nuclear norm. You're taking the negative, doing the opposite of the nuclear norm. But is R is the, so how do you fix little r?
Little r, big which
the little r.
Little r is given, right? It's the rank constraint. So we want the rank of R.
Oh, okay.
Is less than little r. So we penalize the residual, the eigenvalue, the I plus 1 eigenvalues. So make it 0. And then because this is a concave function, this is PR is a concave function. Right. We just then we can linearize it. And by by solving a sequence of a convex problem. So in fact, if the error is negative, then we don't have to. It's always it's always so when we will solve the problem with without the rank constraint, it's always a rank deficient. So you do not have to use any majorization algorithm if the error is actually negative.